Hey everyone, it's your host Russ Altman from The Future of Everything. We have another best of episode for you today. This one is an interview I did with computer scientist and electrical engineer Dorsa Sadigh. We had a fantastic conversation about the work she's doing to train robots to better understand humans. And as nobody will be surprised to learn, it turns out that one key is to better understand human behavior itself. I think you'll be really interested in hearing how we're going to make human-robot interactions work and not be terrible. This is a great episode to tune into again. Please enjoy. Before we jump into this episode, I'd like to ask you to rate and review the podcast. It'll help others figure out if they're interested in the future of everything. When we think about robotics researchers, we don't always think about people who are experts at human behavior. However, if robots and autonomous vehicles, which are really a kind of robot, are going to be introduced into our society at a large scale, they will have to deal with us humans. Now, I love humans as much as the next person, but let's admit we have our quirks. We are not always 100% predictable. Have you ever been driving and been surprised by the decision of another driver? They stop without signaling, or they switch lanes, or whatever. Sometimes we have a set of priorities that are not obvious to others. Have you ever totally misunderstood why a person was taking some course of action, only to learn that they were focused on something entirely different than you were? Like someone sitting at a green light and not moving because they're reading text messages on their phone. We also change our minds a lot. Have you ever asked a map app for directions and then ignored what it recommended? I do that at least as much as I follow it. Sometimes we are very charitable towards others, and sometimes we are aggressive. Our behavior can be very different in different situations. Now, we often need to predict the behavior of those we are interacting with so we can coordinate with them effectively, but our predictions are not always that great. So now try imagining building a robot to operate in an environment not only with other robots, who may be predictable or not, but also with humans who have all the lovable foibles we know and love. This is a real engineering challenge. Those robots have to understand the basics of human behavior and motivation in order to make reasonable decisions that don't put humans in harm and let the robots get their jobs done. I spoke with Professor Dorsa Sadigh about all this. Dorsa is a professor of computer science and electrical engineering at Stanford. She studies robotics, machine learning, and control theory with a special emphasis on understanding the best ways for humans and robots to interact, with a mutual understanding and maybe even respect. Dorsa, you work in robotics, but a lot of your work is focused on modeling human behavior, and I found that fascinating. Why does a roboticist have to become an expert in human behavior?
Yes, I think that's a good question. And I started with robotics and control, and I didn't really care about humans as much. I was working on this field of autonomous driving. And at the time, I was working on safety of autonomous vehicles. And at the time I was really looking at the robotics algorithms, the perception, planning. And it felt like one of the core challenges that we have in the field of robotics, and specifically in the field of autonomous driving, was dealing with humans. So I remember mid PhD, I thought cognitive scientists and psychologists have the answer, and I would go and talk to some of these folks, and I would ask them, well, how do I model humans? Because that seems to be the challenge that we have in a lot of these robotics fields, specifically in the field of autonomous driving, which is what I used to work on at the time. And it seemed like they don't really have those computational models that we need as roboticists, as engineers. And that is what got me excited to think about human-robot interaction. And I realized there's a field around human-robot interaction and algorithmic human-robot interaction that tries to build computational models of humans. And it felt like that is really the core of where the core of the problem is. And that's how I got into this field.
Great. So I guess the general idea is that when robots are out in the world, they're going to, without fail, they'll be interacting with humans, and so that if you have some understanding as a robot of what this human who's in front of you might do and how they might respond to you, it can make you be a better robot.
Yeah, and I think a lot of more classical robotics was about, let's say, pick and place on a factory floor, and that maybe didn't require this interaction with humans. There weren't that many humans around these robots in cages, and those challenges were around manipulation, around actually pick and place. But as we see more robots kind of leaving the factory floors and entering our lives, I think these problems are becoming more and more important. So again, in the field of driving, like we were building these models of how other cars around us drive, and they were totally made up. They were made up models of how other cars probably should be driving. And those were not like those were actually like incorrect models because we didn't take into account the interaction that goes into account when you're trying to change lanes. Like you're actually negotiating with this other car.
Right.
And you need to have like an understanding of this car letting you in or not. And that really depends on the model that you have at that moment. So I do think some of the core problems of like real robotics today is thinking about these interaction problems.
So that's great. So how do you do that? Because obviously you're trained very deeply as a computer scientist and as a roboticist. All of a sudden, somewhere in the middle of your training, you realize, damn, these humans are super important for my success as a robot builder. So is it collaborative with the cognitive scientists, or have you found that their approaches really need to be kind of changed in order to be useful to you?
I think it's a combination of both. I think like this idea of cognitive scientists will come and give us the answers is not the right approach here because like they don't know what type of models we need. Like sure they built like very good models of how humans act and interact and that type of thing, but like it's not necessarily going to be useful for the inner loop of how an autonomous car is making decisions. So that's why I think it needs to be collaborative and we need to understand their field. So a lot of like I do have a lot of collaborations with folks in the cognitive science department. And I think it is important to understand what are their tools and techniques, and there are roboticists who don't look at that necessarily as much, and they just try to take like data-driven techniques. So I think it's got to be a combination, and the two ends of the spectrum are not going to work out. The one end of the spectrum is I just take the answer from cognitive scientists. I don't think that is going to work out because then those models are not going to be feasible to be put within our like planning or perception loops. I don't think the other side is going to work out either. Like the other side, just like trying to like have a data-driven model that just like uses human data and tries to fit, let's say, a neural network to that. I don't think that is going to work out, and we are starting to see some of those challenges today, like in the field of like offline reinforcement learning or learning from suboptimal human data, because there are a lot of interesting suboptimalities in human data that if you don't like think about it carefully, we might ignore and just treat it as any type of data. But like data that comes from human is pretty different from, let's say, like IID data that machine learning algorithms usually assume.
Yes. So just for background, IID it would be means that it's a what is it? Go ahead.
And independently distributed data.
Right. So it's assumptions about the and that's exactly what I want to ask you next, because as a human and as a human driver, when I think about other humans, you go in with a little bit of a model of what they might be doing. But we all have had these experiences of like, holy cow, where did that come from? And, I ride my bicycle a lot, and I'm always trying to make eye contact with a driver because it's like, okay, if you're going to kill me, I want you to look at me before you kill me. So I can see why a purely data-driven approach where you just collect a lot of data is not going to do the trick because there's too many weird things that can happen and they're too rare, so you just won't see them. So I can see how having a little bit of a theory of this might be useful. So I wanted to ask you, like, I know one of the things you study are interactions. How do you model this randomness of human behavior, and what do you tell a robot about that? And do we have technical methods to give them these kind of, I think they're going to do this, but there's a very small chance that they're going to do something crazy?
Yeah, no, I think that's a very difficult like question. So I don't think we have like immediate answers for them, but we have tools that try to address that. So within the field of human-robot interaction, there's this idea of bounded rationality, and it actually comes from behavioral economics. So this idea that humans, they're not like irrational, they're bounded rational, meaning that they have bounded resources, and within those bounded resources, they're actually making very rational decisions, right? Maybe in driving, they have limited time, and with that limited time, they have to quickly make a decision, and that ends up not being the best optimal action.
Right.
Or maybe like they have like bounded attention, like a lot of times, like if you talk to people like who just had an accident and you're like, well, why did you do that? They're like, well, I didn't see the car. I didn't see the car that was coming. And that's because people have bounded attention. Like they didn't actually like pay attention to like the car in the back. So I think there are ways of, in general, like there are ways of modeling these bounded rationalities into our models. That's a common thing that we do. Like we also use ideas from prospect theory, again, from behavioral economics to model these bounded rational behaviors. And I think that is definitely one way to go forward. But you also like mentioned this other issue of like out of distribution data, right? Like even if we
Yeah.
do that, right, there are going to be scenarios we just haven't seen in our data. And the bounded rational model is not really going to capture that because it's like so out of distribution. And the question is, what should we do in those scenarios? And again, like I don't have a good answer for that. I think that's an active area of research, thinking about how to detect out of distribution states and what to do in those out of distribution states. I think is important. Like if I'm driving down the road and there's an ambulance coming down the road and I haven't seen that anywhere in my data, like what should I do? I could maybe detect I'm out of distribution, but like
Right.
what is the right action? Should I like stop in the middle of the road? It's probably not the best action. Like should I follow what other drivers are doing, like following the crowd? That's one strategy. And I think that's a very interesting and important question that you're struggling with today.
So you earlier in one of your answers, you said this word suboptimal, that sometimes humans are suboptimal in their decision making. And you said it's because they don't have infinite time or infinite knowledge of what's going on and they have to make a decision. But I know in some of your work, you've also seen biases in like, on your website, there was something about stacking cups and how a robot who's helping a human stack glasses needs to know things about the human that they might not. So could you tell us about that and what drives that kind of research and what are you learning?
Yeah, so in that work, what we were doing is we were pairing up a human and robot in a dyadic way. They're trying to build a tower together. And the idea
Okay.
is that this robot is not perfect. This robot could totally like fail, like at sometimes, like if as it is like putting towers, like there is some chance of it, like the tower falling and the robot not being good at it. And what we are modeling here is using this idea of prospect theory, the fact that people might not have like the true understanding of risk here, and they might overestimate or underestimate robots' capabilities. And what we are doing is we are basically demonstrating in this work that similar ideas of prospect theory, when we're thinking about high risk type of scenarios, and the fact that people act like suboptimal in those scenarios, that is what we were trying to model. And once we capture that model, the robot could understand that the model is suboptimal in its decision making and take
Huh.
actions that could complement the human suboptimality. So that.
So just to understand that a little bit more, because it really sounds interesting, what would the robot do without the benefit of this theory? And then what might it do instead
Mhm.
with this knowledge of a human who has these expectations that might not be based 100% on a full rational understandanding of the situation?
Yeah, so the idea is that if the robot thinks the human is rational and the human is making like, but rational is not maybe the right word, optimal,
Yeah,
because yeah,
optimal.
yeah.
So has looked at the situation and knows exactly the right
Yeah,
thing to
what is the
do.
optimal thing? And a human should be like the optimal decision maker. If it assumes that it might take a sequence of actions that complement those actions of the human. So you might go for a particular type of tower, maybe that is, so if we were looking at a stable tower and an unstable tower, but like you could get
Okay.
more reward if you build the unstable tower.
Ah,
But the idea is that if the human were optimal, they would realize that the chance of the unstable tower falling is so low that they would still go for that. They would still like
I
take the
see.
risk and build that unstable tower. So a robot who would think that the human is going to be optimal.
Right, because the robot has a full model of physics and can figure out, oh, this is a tough tower, but it's a perfectly good tower. We can build this and we can get all the
Yeah, and
points.
it could like sure it could fall like 0.1% of
Right.
times, but that's not so bad compared to like other reward we were going to get or like the
Gotcha.
benefits of this.
And the human might look at that and say, I don't know,
Yeah.
that looks like a pretty unstable. And so then okay, so tell me if I got this right. So when the robot starts building this risky tower, there might be this unexpected human resistance.
Yeah, so the human is going to be overly concerned about the tower falling,
Ah,
even though like the tower might not fall like that often. But like the idea of prospect theory is that the human is not going to have the right estimate, even though in training, like they might have seen only
right,
0.1% of the time the tower falling. Still,
right.
because they have seen the tower falling, because they've seen the robot could make mistakes, they overestimate that and they're overly concerned about the robot's not
Yeah,
being.
yeah. Okay, so here's a question. Does the robot then stop and communicate with the human and say, hey, I think in this case you need to trust me. We're going to build the really awesome tower. Or does the robot say, fine, I'm dealing with a human. We'll build the less awesome tower because that's what the human
I
wants?
think yeah, that's both of those approaches could be perfectly fine ways of going about this. In this particular work, we didn't have any communication channel, so it was basically the idea of the robot recognizing, oh, the human is not going to like do the right thing for me. So like
Right.
let me model the fact that they're going to be suboptimal and then go with them. But I think that idea of the robot being transparent about its own capabilities or about what it knows and what it doesn't know and communicating that is a very interesting question that I think, yeah, we need to like definitely.
It's super interesting because we've all been part of a team where somebody on the team says, hey, you guys, I'm really good at this, right? Like for whatever reason, I've spent my childhood learning how to do this task and we can just do a really good job. And everybody says, oh, in that case, like, let's take it. So this raises a really interesting issue, which is how much should we expect to train humans to interact with the robots versus training the robots to understand humans? Because you could that kind of came up in the previous discussion because you could educate the human about the robot's capabilities, but I don't know if that's part of your research program. Mm-hmm. So how do you think about who needs to be trained here?
It is actually. So we are looking at kind of like a both way of doing things. So we have a project around active teaching where we are trying to teach a human how to operate a robot. So or how to like basically like even like teleoperate, let's say like an agent. Like I don't know if you've like played this game of Lunar Lander. So it's kind of like a lunar lander that's like difficult to like land. And what we are looking at is like, well, first off, why is it difficult to land? Like what is it that humans are missing? I think that is like that goes back to the issues of bounded rationality too, right? Like why is it that humans not good at this to start with? Right. Like why are humans bad at playing games? Like what is it that makes games challenging? Like and there are different things. Like in chess, again, it's like bounded memory, right? Like I don't have infinite memory to keep track of the tree. Right. But like in Lunar Lander, it's actually a very different thing. It's like bounded time and like I need to like quickly land this.
I need to press a button.
Yeah, I need to press a button. It's not like memory really, it's like something else. So could we identify what it is that humans are missing? And then once we have identified that, could we actively teach them? Like or could you show them like particular skills that help them like land this lunar lander or play chess? Lunar lander is interesting because I'm very bad at it. Like I'm very bad at playing this. And like I didn't know what to do until one of my students was like, at the beginning, you got to press up. And that buys you time to like figure out what to do. And that pressing up, that is like a particular skill that I didn't have. So what we're trying to do is we're trying to identify what are these skills from expert behaviors and try to like teach people these skills like at manageable levels and create drills that kind of like help the person get an understanding of what the robot is trying to do. I think going back to your question of, okay, in general, I'm pairing up a human and robot who is like teaching, who's learning, like how is this co-adaptation happening? I think that's a very difficult and interesting question because they are both like we are pairing up two learning agents, like a human who's learning and a robot who should ideally try to learn too. So we are pairing up two learning agents. They have different learning rates, so they learn at different like frequencies. And the question is like, yeah, how can we think about this co-adaptation? And again, that creates like very interesting like questions. Like maybe the robot should give the human some time to adapt. And then after that, like update its model of like the human's non-stationarities and the fact that they're changing behavior. I think that happens in different like time horizons. One setting is, again, going back to driving, right? Like if you think about autonomous cars today, like my behaviors today around an autonomous car, I think is going to be very different from my behaviors when autonomous cars are just like on roads driving, I don't know, 20 years from now. Like today, like I might like test their behaviors, like I might try to like get close to them, or I might be cautious. So like we don't have good expectations of how this autonomous car is actually going to act. And because of that, like we might act very differently. And if the autonomous car like collects my data, thinking that's how humans drive, that's not a good data because my behavior is also changing. So I think it's important to think about these adaptations.
So many of the things you were saying about the human understanding the robot's capabilities, the robot understanding the human's decision-making, I can imagine all of that is a very complicated. So tell me, what is your approach to this and what kind of experiments have you guys been running in this area?
Yeah, so I think that's a very interesting question. And there has been a couple of different domains that we have thought about these types of collaborations. Like imagine like a human and robot trying to move a table together or play a game of air hockey with each other. So when we think about these types of coordination and collaboration...
And just to clarify, air hockey where they're on the same team or where they're on different teams?
On different teams, actually, on different teams. Yeah, right. But like a fun, not super competitive, fun game of air hockey. Okay. So yeah, in these setups, you got to build a model of the person. Like if you're working with another human, if you're playing a game of air hockey even with another human, you need to build some sort of model of this person. And And today, like a lot of these types of models are computationally very intractable and very expensive because you need to build a belief over like the state of the other agent, like what are they trying to do, like what state are they going. You need to build a belief over the strategy of the other agent, and these beliefs tend to be computationally pretty like expensive to keep track of, like over the whole like run of the game.
Right.
But if you
Right.
think about two humans doing this, like I don't think that is what humans are doing. Like I really don't think people are building high dimensional like belief structures of the other agent when they're moving it like table together.
Right.
Instead, like I think humans are really good at keeping track of low dimensional representations that are enough for coordination, like
Hmm.
almost like sufficient statistics that are needed for doing a task. Like if you're moving a table, maybe I'm just looking at like what forces you're pushing towards me, or you're pulling away from me. Like that might be the only thing that I would try to keep track of, as opposed to like a high dimensional belief.
Yes, my wife and I have moved many things together in the last 35 years, and I have to be extremely careful how I approach those interactions with, as you say, very simple expectations about what I can do and what she can do, and that leads to less arguments.
That's good. That's good. Yeah, so that's basically the idea that we have been exploring. Like, could we keep track of those low dimensional representations as a way of partner modeling? And we have actually demonstrated that in the game of air hockey. So we have a partner modeling
Huh.
approach. It's actually like very scalable, and it like keeps track of like maybe just the direction of the puck, and it automatically figures out what it needs to keep track of. So it's not like we come in and we predefine, oh, you got to keep track of direction. Like the algorithm from data,
Yeah.
it realizes that that is the thing I should be keeping track of.
I love that because when I mean, I haven't played a lot of air hockey, but like one of the first things you figure out is if the person is coordinated enough to hit the puck and get it to go in the direction that they want. And that's a whole different approach than if they're doing it randomly, because then you have no idea where the puck's going to go, and you have to be in a funny way. You have to be more defensive when they're more random. So
Yeah.
so that's great. And you're getting the robots. It sounds like you got the robots to do a pretty good job at this modeling of their opponent.
That's exactly right. Yeah, that's exactly right. So that's kind of the model.
So then I know that your work has also gone to where there's not just two people, or not people, see, not just two agents, a human and a robot, but in these multiple agent situations like traffic, where, well, sometimes collaboration. You did mention collaboration, like for example, when you're merging onto a, well, you said negotiation or collaboration when you're merging in the highway. But in general, I would guess that collaboration is not the right model for traffic modeling. So how do you approach these more complicated multi-agent settings?
Yeah, that's definitely interesting. So one direction that we are looking at in the lab is around the space of mixed autonomy traffic networks, where we have some number of autonomous cars, some number of human-driven cars. And it is true that, yeah, the interaction there is not fully collaborative. It's not fully competitive either.
Right.
Like it's not like we definitely don't want to have like accidents. So
Right.
it is really like a general sum game, like that models this interaction. But at the larger scale, right, we are looking at how we could take actions, like how autonomous cars can take actions that influence the other drivers into responding in particular ways that is useful for
Huh.
some societal objective. So we're looking at like congestion, traffic congestion, and we're thinking about how we can plan for our autonomous cars routing decisions to actually bring down traffic. Like if you have the option of
Huh.
going from Palo Alto to San Francisco and you can take 280 or 101, like the idea is that could we get our autonomous cars to make decisions that influence humans to take a different route, and then actually bring down congestion based on that.
So because of just my life, I wind up on some highways a lot, and I notice that there's certain driving habits that lead to slowdowns much more than other. Do you think we could program cars to actually drive in a way that they reduce the chance of like a 0 mile per hour section of the highway that just sometimes pops up for random reasons without an accident, without anything?
Yeah, no, there's actually a lot of work around this, and there is work that shows that
Huh.
you could use autonomous cars, not from our group,
Right.
but yeah, there is actually like work that shows that you could use autonomous cars to bring down congestion, like on a single road, and reduce these types of congestions that are caused by just simple slowdowns of vehicles. So yeah, definitely like autonomous
Yeah,
cars.
that could
can
be a huge advertisement for why we these mixed situations. Well, I don't want to end without talking about your work in healthcare. So I know you've done some things relevant to healthcare. Assistive technologies is the general umbrella. So tell us about those.
Yeah, so in general, we're interested in human robot interaction. And I think one of the core applications of human robot interaction is in healthcare. Like when we think about assistive technologies, like assistive robots that can help people with various types of tasks. And one domain that we're actively working on is like assistive teleoperation and robotics. So how do we get a robot to help a patient like pick items or help them like feed themselves, which is a very interesting problem. And again, I think it is a very interesting robotics problem because how do you like pick up food items in ways that they don't like how do you pick up a banana and make sure it doesn't fall? I think that's a very difficult problem.
And then get it into somebody's mouth. Yeah.
Right. Yeah. And then that transfer is like a fully like interaction problem with a person. And there are a lot of safety concerns. Like a fork is coming towards you. Like how do you make sure that you transfer that food in a way that's safe and comfortable and put the right forces into the person's mouth? And that is a direction that I'm really excited about and we're actively working on. And I think a lot of algorithms that we are building can actually be showcased like in this particular application.
Yeah, it's anybody who's fed a 2-year-old might have good insight into this because it's so random and you really don't want to poke the fork in but the kid is extremely random. I have some recent experience with this. Is the healthcare system ready for this? Are people open to this? Do you see excitement from the doctors who you talk to, or are people afraid of the robots still?
I think, yeah, so I don't think it is there yet because like our systems are really not there yet. There are a few companies even who are trying to like do similar types of feeding tasks. We also work with like patients with disabilities, and a lot of these patients are actually like very excited about this technology and like they tell us like what they want and what they don't want out of the robot. So that part of it is really exciting. So I think a lot of robotics companies are excited about this and pushing this, but we still have like a long way to go. This is still like in the research kind of side of things, but I think we're going to get there.
Thanks to Dorsa Sadigh. That was the future of human-robot interactions. Thanks for tuning into this episode. We have more than 250 episodes in our archive, so you have instant access to a broad range of discussions on an amazing variety of topics. If you're enjoying the show, or if it's helped you in any way, please consider rating and reviewing it. That'll help us understand what you're experiencing with the show, and it'll help get the word out. You can connect with me on X or Twitter @RBAltman, and you can connect with Stanford Engineering @StanfordENG.